وقت الكلاس, yes. So طبعا we'll start maybe at maybe 12:30 or 12:35, depends on the time that I will allocate for the quiz. Okay. طيب. So let's start now. So this is the second topic of electronics 303, which is the frequency response, where we want to study the frequency response of amplifiers. And basically we'll study the frequency response using some tools, and these are some of the tools. We need to review the Bode Plot, how to find the poles, zeros of the system, and actually we'll do only the poles. The zeros will not do the zeros, so we'll find the poles of the system, and then we'll also to be able to do that, we need to make a high frequency model for the transistor, and this is something new for you guys. Because what we used to do before, it is just a low frequency model where we have only a voltage controlled current source and RO. But now we'll add the capacitance or the internal capacitance of the transistor, and that's what we call the high frequency model. Then we'll talk about the Miller's theorem, because obviously we'll have some floating capacitors, and we want to apply the Miller theorem to analyze those capacitors and simplify the circuit, the analysis. And then we'll study, of course, throughout these or having these tools, we can now study the frequency response for all configurations, the common source, common gate, and common drain, and their counterparts with the BGTs. And then we'll study also the frequency response of some multi-stage amplifiers. So this is basically our second topic agenda in general. Type. We talked about amplifiers before, why we need them. Actually, we need them to amplify signals, weak signals, and also it acts like, or it can be used as a building block for other sub-circuits like oscillators or filters. We'll see later we can build filters or oscillators around an op-amp, and the op-amp is nothing but an amplifier. Okay, and we talked about the macro model for the amplifier. We said the macro model, the simple macro model for any amplifier, we can represent it by Rn here, by a voltage controlled voltage source, and an R out here. Okay, if I am talking about a voltage input, voltage output, or what we call voltage amplifiers. Okay, so if this is the case, we have an intrinsic voltage here, and let's call this one Vi. Of course, this is, let's call it V output dash, and this is your load. So the load will be connected here, and it's not part of your amplifier that you are buying from whatever or you are doing, but you need to include RL when you design the circuit, because the overall voltage will be, or the RL will affect your overall voltage. And it is the same case for R signal. So the R signal needs to be considered when you design your amplifier. Okay, but in the macro model, we have only three parameters. We have the input impedance, Rn, right? So we have Rn, we have R out, and we have the amplification or the gain of the circuit. So now we can decide which R signal we can connect to the circuit, which load we can connect to the circuit without kind of affecting the overall performance. But we don't know if the amplifier will sustain the operation for a lot of for wide spectrum of frequencies. So this is true for some frequencies, but if you go, for example, for higher frequencies, maybe gigahertz or terahertz, will this amplifier still can amplify the signal with the same gain? The answer should be, the answer obviously no, because when you increase the frequency, you will have, because of the effect of capacitors in the circuit, those capacitors will kind of attenuate the signal, and that's attenuation. In another word, we can say it is a gain reduction. So to do that, to be able to know the frequency response of the amplifier, or to know the speed or the bandwidth of the amplifier, we need to study the frequency response of the amplifiers, including capacitors. Okay, in this model we don't have capacitors, but we need to include capacitors and see how we can study or analyze the circuit. So what we are interested in this topic, in this in frequency response topic, is just to quantify the bandwidth of the amplifier. And if you know the bandwidth, you know the speed of the amplifier. And I'm talking about here the amplifier, where we can start from very, very low frequency, maybe sometimes 0, which is DC, to whatever the high frequency you have. And if you have, for example, an amplifier that is operating at maybe 1 gigahertz, it is as if you are saying the speed of the amplifier is 1 gigahertz. تمام؟ فهم وجهان لعملة واحدة. الباندويث والسpeed في الامplifier, it is the same meaning. But the bandwidth in the high band pass filter, for example, it's something different. Okay. So to quantify the speed or the bandwidth, you need to do the frequency response, and this is what we are doing in this topic, inshallah. For others, which is the dynamic range, yes, تفضل.
How can we connect the speed and the bandwidth mathematically?
No, we will not connect them to the macro model. This simple model is just enough for us to see the gain, the input and the output impedance. But later we will add the internal capacitors to the circuit, not the macro model, to the circuit. And then we'll say, okay, we have an amplifier, which is this one, but we'll have 2 poles or 2 corner frequencies. So we'll just quantify FL and FH. يعني خلينا نقول نحطها كلام. تمام. No need to add capacitors here or there. The macro model, the simple macro model that we have here is enough to quantify the 3 parameters. And then for the bandwidth, which is FL and FH, you just write it down as another feature for this amplifier. Okay? طيب. طبعا for others اللي هو dynamic range, we talked about the dynamic range in very briefly when we talked about the differential amplifier, but in general we can it depends on the circuit, and also the power consumption, it depends on how much the drain current you are supplying, for example, to your amplifier. Then you multiply that by VDD, which is very simple, and then you may also add, you do the same for all internal sub-circuits, and then you can find the power consumption. We'll not do this too. Actually, what we are doing, we are just quantifying the bandwidth. Right. For the basic amplifier stages, we know we have 3 different basic stages. We have the common source, we have the common gate, and we have the common drain. And of course, we have also the degeneration with the common source. So you may apply a resistor to the source, and that's a common source plus a degeneration. And we know the gain of these configurations. Of course, when we analyze the frequency response, we will remind you again and again about the gain of these stages. And we'll study the frequency response of these stages. Right. So answering this question, why you are interested, or why we are interested in studying the frequency response, actually we want to quantify the speed of the amplifier or the bandwidth, in another word. Okay. And okay, so let me ask you guys, is it better to start or to study the amplifiers in frequency domain or circuits in frequency domain or time domain? Which one is better, or which one give you I mean, more insights, or like what is the difference between doing frequency domain and time domain analysis? What do you think?
I think
frequency
is better.
Frequency is better. ليش يا شباب?
It's easier mathematically to manipulate.
Exactly. If you have more capacitors in the circuit, now you have a lot of differential or equations. If you say, so it's much better or much easier to analyze the circuit with the frequency domain, because now you are doing Laplace, which is 1 over SC for the capacitors, and you deal with it as Z, like an impedance. So it is much easier, and also give you more insights in the like the operation of the amplifier over a wide spectrum. So you can analyze the circuit at one specific frequency. that's fine. But we do that when we are dealing or when we are interested to find the transient response at that particular frequency. But in reality, what we have a lot of frequencies. We have a signal with a lot of frequencies. So you want to see the response of the amplifier over a wide spectrum of frequencies. And that's why this is another reason why we do frequency domain analysis. Let me remind you that S is, when we deal with S, we are dealing with S as a sinusoidal signals. So we'll deal with it as J omega. It's not J omega plus constant or plus A, which is the real part. So we are dealing with it as J omega, okay? And let's see how we can do the frequency response. We have two approaches, one or two steps. One, if you want to study the frequency response of any circuit, and let's assume we have this simple RC circuit. طبعا we'll change the C to 1 over SC, okay, to make it much easier to deal with. So first, you can take just like a general overview. What is the response of the circuit for the extreme frequencies? And what we have, extreme frequencies, we have if either 0 or if goes to infinity. We have two extremes. Tamam? So we'll say, okay, what will be the response of the circuit when f equals to 0? In another word, what is V out when f equals to 0? What do you think in this case?
إذا دي سي يعني يا دكتور الكاباسيتور راح تصير open circuit.
It is open. No. Regardless. So this VI, let's assume it is sinusoidal wave. Okay. So this one is AC signal. Perfect. So this is AC signal. Okay. And now you have a frequency of 0, almost 0. Yahya said, okay, now you have a DC value. So the DC value will be 1 over, the impedance of the capacitance will be 1 over 0, and that's infinity. It means this one will be open, okay? And the output will be the same as the VI. So V output will be the same as VI. Do you agree? Because this one is open now.
Yes, yeah, Victor.
But when f equals or approaches infinity, what will be the output? Following this one here, 1 over C.
The voltage across the capacitance.
Which is, let's say you are doing extreme frequency, which is infinity. 1 over SC equals what? At infinite frequency.
1 over CS?
SC. So this is the capacitance, okay? And now your capacitance, of course, this is J omega C, right? And this is nothing but J2 by FC. So if now goes to infinity, what will be this term will goes to 0, right? Why I am doing it should be much better horizontally. Okay, so this one 1 over SC. This one will be J omega C, and this one will be J2 by FC. And if your frequency goes to infinity, what will be the value or the magnitude of this one?
0.
0, exactly. So if this one 0, it means this one is shorted, right? If this one is shorted, your V output now is 0. So of course, you are thinking that if you are drawing the V output versus frequency, you should get something like maybe if this is your VI, so this one will be VI, and then at the end of the day, it will go to 0, right? Regardless of where it goes to 0 now. Make sense, Shabab? So this is one step. You just draw the extremes. If you have a 0 value for the frequency, which is DC, what will be the shape or the pattern or the behavior of your circuit? The same when it comes to the infinite frequencies, just like thinking. Then we are interested to know where this one is trying to, starting to decrease. تفضل يحيى. عندك سؤال؟
لا يا دكتور.
Okay, So to do that, we can analyze the circuit, and usually this is we can apply a voltage divider rule, right? VDR. So the V output, I'll do it very quickly here. The V output over V input, which is the transfer function of the circuit, will be what? Will be 1 over SC plus 1 over SC plus R. Okay, so we are doing very simple kind of linear equation here. And if you do this, this one will be 1 over what? 1 over SCR, right? And to get the magnitude here, and usually we are, so this is 1 VI, the transfer function will be 1 plus omega squared C squared R squared, right? By the way, so this is the transfer function, and we define the corner frequency here to be the value where you have a reduction of minus 3 dB from the gain. Okay, so this is kind of a standard that we use. So if you when you have a minus 3 dB reduction in the gain, that means this is your corner frequency. Okay, let's call it FC. So this is the corner frequency that we are looking for. So when we have minus 3 dB reduction, minus 3 dB reduction, it means 1 over root 2 exactly. Okay, so if you do that, if you take this one as 1 over root 2, the same, because 1 over root 2 is what, ya shabab? Minus 3 dB when you transfer it to dB. Okay, so 1 over root 2, it is the same as if you are saying the omega squared C squared R squared equal to 1. And it is the same as if you are saying FC equals 2 by CR, right? So let's call this one FC. Okay. And this is second step. So second step is to find the minus 3 dB for the system, which is the corner frequency of the system. And by the way, we usually do that because it acts like the half power point. Because beyond that, not only we have a reduction in the gain, but also we are losing more than half of the power. Okay, and try to convince yourself or try to find an answer for this. I mean, to relate this one together, which is the half power point. Okay, so this is a point where you have, if you go beyond this point, you are losing more than half of the power. Okay, you can relate that when you are using voltage, because 1 over root 2 now we have a reduction of 1 over root 2, and assuming R is constant, and the power you're using power V squared over R, which is half of the power will be at that point. Tamam? So also another way of doing it, we can do the time constant of the circuit. So what is the time constant of this capacitor here? What is the time constant of this capacitor? And the time constant usually we ignore the excitation voltage or current. The time constant will be what? Tau. تذكروها يا شباب ولا لسه؟ التايم constant لما يكون عندك capacitor connected with parallel or what in series of the resistor, then you take the R equivalent of or the equivalent resistance seen by that capacitor, you multiply by them, multiply both, you'll get ايش؟ the time constant. طبعا التايم constant ايش يفيدنا فيها يا شباب؟ in general معلوماتكم ايش التايم كونستانت؟ لما اقول لك التايم كونستانت حق الكاباسيتور 1 second, what does it mean؟ ايش معناها 1 second؟
يفيدنا في الترانزيت ريسبونس.
تفضل ابغى اجابه، تفضل مؤيد.
The time it needs to reach the fifth of its initial charge, I think.
ممتاز. يعني علشان اشحن الكاباسيتر بشكل كامل I need كم يا شباب؟ إذا قلت لك الكاباسيتر التايم كونستانت فور ذيس سيركت، طبعا التايم كونستانت فور ذيس سيركت لازم يكون في كاباسيتر وريزستور في الموضوع. أقول لك التايم كونستانت حق الكاباسيتر هذا 1 سكند، معناته أنت على طول باي ديفولت تقول خلاص علشان أشحن الكاباسيتر هذا I need at least 5 seconds اللي هو 5 time constant. تمام؟ 5 times the time constant. Right? And also we have interpretation for this one in the frequency. This is the corner frequency of the system. The time constant, the inverse of the time constant, which is 1 over tau, it is the corner frequency of the system. So this is nothing but 1 over tau, okay? And we have a lot of analysis. We can relate these two things together. But in general, if you are interested in finding the corner frequency of the system and you have a simple capacitor and resistor, just find its time constant and then you divide by 1 over the time constant. Tamam? Okay? Also, we define here what we call the bandwidth. So what is the bandwidth? The bandwidth is nothing but FH, the maximum frequency we can use. طبعا beyond the maximum frequency عندنا الامبليفاير useless. ما اقول useless يعني كلمة صعبة هذه useless. خلينا نقول we don't normally operate our amplifier beyond FH. فالFH هذه الهاي الماكسيمم اللي هي عندنا تعبر عن ايش بالسمبل هذه سيركت. وين الFH؟ عبارة عن ايش؟
الFC.
الFC exactly. So the bandwidth, this is just a definition. The bandwidth is the maximum, or it is the range of frequencies you can operate the amplifier within that range, and it can be quantified using FH and FL. So the FH minus FL, this is the bandwidth. اللي هو maximum frequency, corner frequency, subtracting or minus the minimum frequency you can apply. And for this simple system, how much is the bandwidth, Shabab? What do you think? The bandwidth here will be FC, right? Because FL here is 0. You can go from 0. You are starting from 0. You don't have any problem. تمام يا شباب؟ إذا أعطيتك الجراف هذا وطبعا مرسوم بالفريكونسي دومين I specified that this is your corner frequency here. It means the bandwidth here is FC. طيب؟ أتمنى وضحت يا شباب. وضحت؟
هذه يا دكتور هذه رسمة اللو باس فلتر.
It is a low pass filter. Exactly. It is a low pass filter, and if you exchange ال R with C بتصير high pass filter. تمام؟ طيب, let me ask you now, how can I maximize the bandwidth? احنا بالاخير نحب انه يكون عندنا bandwidth عالي بالامبليفايرز. طبعا depends on the application, but in general it can be a true statement. So how can I maximize the bandwidth?
You can increase either the resistance or the capacitance.
Exactly. So you can play with RC here. Increasing RC will decrease the bandwidth and vice versa. So you need to decrease the RC and then you'll get a good bandwidth or you're maximizing the bandwidth. Okay? طيب. This is for you, Shabab, self-exercise. I wanted to go over to see how you can, for example, derive or sketch the frequency response of these circuits. تمام? And we have only one time constant for each one. Right. If you have any problem with this one, let me know. This is like kind of basics. I guess this is from 213 of your class 213. Right. For our amplifier, we have the typical amplifier response. This is the one we are talking about. So, and of course, I am drawing the voltage gain, which is V output over V input. Okay. Over the frequencies. And of course, you can modify the circuit here if you want this one here to be the gain, which is over VI, and this one will be 1, right? So it is the same thing. So in the frequency response, we are drawing a shabab voltage gain or current gain, tamam, versus frequency. طبعا we have a lot of parameters we can draw. We can draw the impedance, the whatever, but what we are interested here is the gain over or versus the frequency. Tamam? And we have this kind of general behavior. يعني دائما وابدا you have this kind of behavior in the frequency response. So you'll have some mid band. الميد باند يا شباب هو المنطقة اللي احنا نتكلم عنها from our EE303 from our classes until today. So we know that مثلا common source we have a minus GM R0 parallel with RD, for example. So this is the mid-band region, or the region that we want our amplifier to be, or we want to operate our amplifier within this range. Okay, so this is what you need, ya shabab. The mid-band gain is already studied, and we know how to find the mid-band gain. معناته أنا في الميد-band I exclude the effect of all capacitors. تمام؟ معناته الكابلينج ايش يكون؟ الكابلينج كاباسيتورز بيكونوا shorted والبارازيتيك كاباسيتور بيكونوا open as if they are not there. تمام؟ This is the mid-band region. But then if you go lower in frequency, and I am going to the left this way, you will see that the gain is decreasing based طبعا depends على السيركت حقك. ممكن يكون almost constant up to 0. تمام؟ And this is the case with the differential amplifier or the operation op-amp in general. But let's say we have a single transistor amplifier. If you are going to the left, decreasing the frequency, you will see that the gain will decrease. And this is what we call low frequency band. Okay? And I will find the gain here, and the gain will be the gain of the circuit, which is the FL, the LF, not FL, the LF, low frequency band. تمام؟ متى يكون low frequency يا شباب amplifier؟ بعد ال FL. When you hit the FL, now you are decreasing. تمام؟ You are even before that, معلش, even before that. بس الآن للattenuation, I can find the attenuation or the gain at this point, and that's nothing but your ALF. You'll do the opposite when you do increase the frequency. And of course, you will hit that point, which is the FH. And that point will be the maximum frequency you can apply to the system. And beyond that, we are dealing with high frequency band. And the gain here, we can call it high frequency AHF for the gain of high frequency. تمام؟ طبعا you can define it anyway. I mean, these are just notations. واضح؟ فمعناته عندنا ميد باند، السيركت شغاله زي الالف، هي المنطقه اللي انا بشغل فيها السيركت. But once I reach around the FL، انا اتكلم عن low frequency band، معناته عندي attenuation. لما اقول attenuation يا شباب معناته الجين عندي صار له reduction. بدل ما كان الجين عندي 10 بالبدايه بالميد باند، و around FL بيكون الجين كم تتوقعون؟ اذا كان الميد باند 10 10 volts per volt. What do you think of the gain here at this point?
7.
7, exactly. 7 or 7, which is what? Which is 10 over root 2. تمام؟ احنا قلنا النقطة اللي عندها ال FL وال FH بيكون ايش؟ الجين divided by root 2. فعندك 10 تقسيم 1.404 or 10، عفوا الجين مضروب. It is the same thing as if you are saying الجين مضروب في ايش؟ 7.707. It is the same thing. فإذا عندك الجين 10 معناته أنت النقطة هذه طلع عندك الجين 7. فإذا عندك input voltage قيمتها 1 volt, at these 2 points you will find it to be 7.07 volts. Okay? بعد كذا طبعا راح ينزل الجين، راح ينزل يسار ويمين. And you are talking about low frequency band and high frequency band. Okay? طيب. This is in general. Now, why we have attenuation, or why the frequency, the gain is decreasing at the low frequency band? It is due, شباب, due to coupling capacitors. Okay, so the gain here falls down because of the coupling and bypass capacitors. لو تلاحظون اتوقع ما عندي no, not this one, not this one, not this one. Oops, خلاص بيكون كلام طويل. عموما خلوه في بالكم اللو فريكونسي راح يكون عندي متى؟ لما يكون عندي coupling و bypass capacitors في السيركت. Okay, but in the high frequency we are talking about the parasitic capacitors and we will study them, which is the high frequency model. فالآن هنا نتكلم عن high frequency model, and for the MOSFET we have CGD and CGS capacitors. Here we are talking about the coupling capacitors اللي هي بنلاقيها بالعادة لو رسمنا الcommon source amplifier. As such, usually we have some coupling capacitors here. Okay, let's assume we have this kind of structure. Okay, and this is CS, this is C2, this is C1. What we call these ones, this is what we call coupling capacitors. Why we call it coupling? اللي هو C1 و C2. We are coupling the input and the output to the amplifier. لاحظ ان الامبليفاير اللي هنا هو ايش؟ هو اللي اشتريناه من السوق او اللي وات ايفر، طبعا including CS. This one. This is what we have from the market, from يعني we buy it. And then we couple our input and output using what? Using C1 and C2. So these are coupling capacitors. ايش معنى coupling؟ ارتباط. انا اربط الانبوت والاوتبوت بالامبليفاير حقي. So these coupling capacitors will attenuate the gain when it goes or at low frequencies. So we need to take care of them. ابى اجيب الفاليو، هل الفاليو حقها 1 مايكرو فاراد ولا 1 نانو فاراد ولا 1 فاراد؟ طبعا ما في شيء اسمه 1 فاراد بالالكترونكس هنا، في السوبر كابس، بس in general احنا نتكلم عن very low capacitance value. But yes, so the gain will be ايش؟ will be attenuated due to these effects or these the coupling capacitors. And also not only that, not only the coupling, but even the bypass capacitor. Bypass capacitor which is CS. By the way شباب, why we call it bypass? الكابلينج اتفقنا انها joining الانبوت والاوتبوت or coupling الانبوت والاوتبوت to the system or to the amplifier. ليش سميناها bypass؟
لأن استخدمنا يا دكتور الكرنت source to be running from DC point of view and to demolish it from AC point of view.
ممتاز جدا. Let me put this one here again. Let it to be a resistor. Okay. تمام. ما في مشكلة. So it is the same thing. يحيى, as you said, we want the AC, the source of the transistor from AC point of view. We want to bypass it through the resistor, or in another word, we want to connect it to ground. Okay. So that's why we call it bypass capacitor. So the effect of gain reduction in the low frequency is due to the coupling and bypass capacitors. And the reduction in the sorry guys. And the reduction in the high frequency is due to the parasitic capacitors, and we'll talk about this one when we discuss the high frequency model. Any questions, Shabab? In general, we need you to know the general behavior of the amplifier.
Yeah, Doctor, why do we quantify FL and FH at minus 3 dB? Why don't we quantify them at 0 or minus 6 dB?
Okay, so beyond, طبعا in general, this is like a standard that we agreed upon, تمام? And we are interested, maybe this is what we call half power points, تمام؟ معناته الباور هنا طبعا you don't want to operate your transistor, your amplifier in this region. You want to make it here, but this is kind of the maximum limit you can go. تمام؟ خلينا ناخذ the maximum limit of the amplifier. طيب, because beyond this one you are losing more than half of the power of the signal. يعني you are using مثلا I think, yeah, and even from, this is from power point of view. From the gain point of view, you are reducing the gain to 1 over √2 or 0.707. طبعا 30% reduction كأنها صح؟ فعندك 30% reduction. كلامك سليم. ممكن نحن نتفق يعني يوم من الأيام ونقول خلاص we want to increase this one to be مثلا 10% reduction in the gain. Okay, and that's fine. But what we agree upon, it's like the bandwidth definition. The bandwidth definition will be the 3 dB point of the frequency response gain. تمام؟ فإحنا نتكلم عن definition موجود الآن standard الجميع يتفق عليه. طيب، لكن كلامك منطقي ولوجيك إنه I don't want to lose my signal. I don't want to use the like 30% of gain reduction شيء كبير جدا. So that's why we want to maybe use less than that. يعني مثلا if you have 1 gigahertz of bandwidth, you may want to use, for example, you want to operate it at 850 megahertz instead عشان تكون في السيف سايد. تمام؟ وهذا الابلكيشن اذا جاك ابلكيشن مثلا وعندك different amplifiers, الابلكيشن requires 1 gigahertz operation. تمام؟ Let's take it from this way. يعني let's take it in the reverse. So the application requires 1 gigahertz of operation. And then you have different amplifiers. You find it in the market 1, 2, and 3. تمام؟ واحد يشتغل exactly at 1 gigahertz. تمام؟ الثاني at 1.25 gigahertz. الثالث at for example 2 gigahertz. Which one you should select?
لازم اعرف يا دكتور الرينج حقي.
لازم تعرف الرينج حقك. انا عندك الاوبريشن حق الابلكيشن قال لك والله انا احتاج 1 جيجا هرتز.
اكيد باخذ
3 different amplifiers. What's happened? You still see it يا شباب ولا قام؟
لا راحت يا دكتور. كنترول زد يمكن تطلع.
غريبة. طيب فعندك الابلكيشن.
I'm going to choose 1 gigabyte of course.
الكلام المنطقي الثيوريتيكال والايديال يقول انك تاخذهم جميعهم صح؟ ما عندك اي مشكله فيهم كلهم. الامبليفاير اللي يعطيك 1 جيجا هرتز should be fine. 2 جيجا هرتز should be fine. 1 2.5 should be fine صح؟ بس in real life we don't do that. We usually have some safety margin. So if you are using 1 gigahertz or you want to have 1 gigahertz operation, it's much better to use much higher than 1 gigahertz. I mean, not much higher, slightly higher than gigahertz. So maybe we use 1.25 or 2 gigahertz. And then the second question will say, what is the other parameter? What is the performance of the 2 gigahertz and 1.2 gigahertz? Okay, so the takeaway from here, we don't want to operate our amplifier at exactly the FH because we are losing the gain. But regarding the definition of the bandwidth, it's like a standard. We are using the 30% reduction in the gain as a standard to define the bandwidth. تمام? In other words, when it comes to the power, you are losing half of the power in that point, and beyond that, you are losing more than half of the power. Okay? طيب. So let's continue, guys. طبعا I'll not discuss the Bode Plot. I wanted to go over these slides, the Bode Plot, just a review for you why we need Bode Plot and what's the difference between the linear and the Bode Plot. How we can plot or use the Bode Plot to plot the transfer function. I need just to know that we can define if you have a transfer function here. I don't know what is happening with that application 1 gigahertz or يعني دائما تطلع. Anyway, the transfer function here we can define the poles and the zeros of the system. Okay, the poles will be the roots of the d0, the denominator here, which is ds equals to 0. Or in another word, now the voltage goes to infinity, right? The voltage at the pole will be almost infinity. The zeros of ns, which is the root of ns, and it is as if you are saying the voltage at ns or at the zero will be what? Will be 0. So as if you are nullifying the voltage or the output voltage. Okay? So these are the poles and the zeros of the system. And we can, I believe you can analyze or you can find the poles here. Let's find the zeros, Shabab. What do you think? What will be the zeros here of this system, of this transfer function?
0 and minus and 10.
Exactly. And the second one, because you have squared, that's why you take the root of 100. So what about the poles, Shabab? Or let me ask you, how many poles we have? Oh, we have it here. I don't want you to see this one.
We have
how many poles we have, Shabab?
3 poles.
3 poles, right? So this is a third order system. And what are the poles?
2 complex and 1 real.
Exactly.
Yeah, so we can see it from here. So this is just a reminder of these basics, and we will use. Okay, this is just also another Bode plot. Okay, so let me go back to graph of the behavior of the frequency response or the voltage gain. We have the voltage gain and we have the frequency here. So this is the midband gain, and I am focusing on the midband and in the low frequency region. Okay, so what is the behavior here? It is nothing but what? If you do this, what is the behavior? What is the pattern here? Is it low pass or high pass?
This is high pass.
It is high pass. So we may approximate this one to be a high pass filter, and then the high pass filter frequencies or poles can be found using what? Using time constants of the capacitors. So what we need to do in the low frequency, we go and study each capacitor or the pole associated with each capacitor alone, okay? And then at the end of the day, you can find the AL, the gain at the low frequency. And by the way, Shabab, it is an approximation here. I am kind of not finding the zeros of the system. I'm finding only the poles of the system. Maybe sometimes I will get some zeros, but I will get some zeros at high frequency, but we'll ignore it for now. So still, this is a good approximation here. So we want to quantify FL. Okay, we need to find the FL. فالآن يا شباب ايش نحتاج نسوي؟ We go to for C1 and C2, for example. If we have two capacitors, C1 and C2, we will study the time, or we'll find the time constant for C1 alone. تمام؟ طبعا ايش معنى هذا الكلام؟ معناته C2 ايش بيصير له؟ بيصير له شورت سيركت ولا اوبن سيركت؟
What again?
إذا عندك خلونا ناخذ السيركت maybe. So maybe let's take this one. Let's take the circuit. Let's find the poles of this system. The pole of this system, which is the time constant of this system. What is the time constant of this circuit? What is tau يا شباب؟
RC2.
Exact. Which RC ايش هي؟ السي عفوا ايش هي السي؟
اللي هي in parallel.
In parallel. They will be in parallel because you are deactivating the voltage sources. Okay, this is the first step. So in the first step, as I said here, you need to deactivate. So we set all sources to 0. So we deactivate the sources, and then if we deactivate VI here, we'll see that C1 and C2 will appear in parallel, and the only resistance they can see is R. So this one will be your time constant. And of course, the pole here, or the corner frequency associated with this one, will be 1/2 by tau. واضح؟ Is it clear يا شباب؟ فأول شيء تطلع التايم كونستانت وبعدين تطلع البول. طب عشان أطلع time constant, I need to deactivate all sources, and then we'll see if you have two capacitors. طبعا both those two capacitors, if they contribute to the same pole, ممتاز. As we have here, we have only one time constant. But if you have two different capacitors at different nodes, then they will have 2 poles in the system, or 3 poles. It depends. What about this one here? What is the time constant seen by this circuit? For this circuit? Or what is the pole for this circuit? ايش الكونديشن اللي عندنا الأول يا شباب؟
Deactivate the source.
Deactivate, exactly. So this one will be connected to ground. Will be shorted.
R1 and R2 in parallel.
Exactly. So time constant will be, do we have 2 different capacitors ولا C1 راح يكون parallel مع C2?
Parallel.
In parallel. So this system, actually we have only one pole. So C1 will be in parallel with C2, which is plus, right? And then both of them will be in parallel with R1 and R2. And the corner frequency or the pole of the system will be seen at this frequency, C1 plus C2 with parallel R1, R2. Okay. احنا الآن we are building knowledge هنا عشان نفهم كيف نسوي البولز والزيروز. عفوا البولز of the system. What about this circuit?
Deactivate وال L1
exactly.
is in parallel.
L1 will be in parallel with L2, and the L, which is the inductor, will see only R, and you'll do the same for the next one. So it should be clear. But by the way, we don't usually do inductors here because what we have only capacitors in most of our electronics circuits, and in the medium mid band and also low frequency. طيب. So maybe this is just a reminder of what we have discussed. Yeah, and also one thing more here. This is what we call the gain bandwidth product. Okay. طيب, we have the midband gain, which is AM. زي ما اتفقنا شباب, ال AM اللي هو نحتاجه, وال AM اللي نحتاج الامبليفاير انه يشتغل عنده. Okay. ال ALF and AHF, these are beyond the operation of the amplifier. تمام? This is just for you to know the attenuation at this point, for example, at this point here or this point there. But we are not operating our amplifier at these points. Tamam? Okay, so this is one. So AM is the gain of the amplifier. Tamam? We will define it and we will find it the same way we do usually. And then we define this FH and FL depends on the value of the gain, which is gain over ρ2. And if you have the bandwidth, we define another parameter, and this is very interesting parameter. You will find it in most of the data sheet. This is what we call the gain bandwidth product. Okay, so the gain bandwidth product, and sometimes they call it FT, it is what? It is the gain from the name, the gain multiplied by the bandwidth. Okay, so the gain bandwidth product will be almost constant. Okay, لاحظ أنا أستخدم الكلمة almost constant لأنه in the lab, if you do it in the lab, you may have some you may need to do some approximations, but it is almost constant theoretically, but not always, but this is good measure for us. الجين bandwidth product بيكون مثلا عندك ثابت, it is a feature for the amplifier. فمثلا انا ابيع عليك امبليفاير واقول لك الامبليفاير الجين باندويث برودكت حق الامبليفاير هذا 1 ميجا هرتز, which is the same as the op-amp 741 اللي نستخدمه احنا باللاب. تمام؟ فلما نستخدم ال 1 ميجا هرتز with gain of 10, اذا كان الجين of 10, how much of bandwidth I may get from this amplifier if the gain bandwidth product constant? What do you think?
100 giga.
100K. So this is the maximum bandwidth I can get. إذا عندك application قال والله الجين عندي 100, I need the gain to be 100. Using this amplifier, which is 1 megahertz of gain bandwidth product, the maximum bandwidth I can do is what? Is 10 kilohertz. And so on. فهي ميجر لك يا شباب إنك تعرف وتقدر is it a good amplifier to get or to buy or not. يعني زي لما يجي واحد يشتري أي شيء بالسوق له feature هذا الشيء. تمام؟ فعندنا الجين باندويث product is very good measure. It's a constant, almost constant. تمام؟ And from there we can estimate the bandwidth of operation of our circuit based on the gain requirement of our circuit or our application. واضح؟
يعني يا دكتور مثل ما
yes.
مثل ما تكلمنا في differential amplifier, there was a trade-off between the gain and the linearity. We have trade-off here between gain and bandwidth.
بالضبط. إذا زودت الجين نزل عندك الباندويث. أوكي, لأنه الاريا بنخليها constant almost. طبعا for the same amplifier. يعني مثلا you design an amplifier to have certain oh it is 52. طيب خلاص بنقفل يا شباب. So certain behavior like this one. This is your amplifier. then with this amplifier, if you increase the gain, the bandwidth will decrease. So this is what you may get. You may get something like this. Okay. So the new FH will be here. The new FL will be here. Okay. Because we want to keep الجين bandwidth product almost constant. هذه مش احنا نقولها يعني هذه trade off الموجود زي ما تفضل يحيى. So if you increase the gain, the bandwidth will decrease. If you do the opposite, if you decrease the gain, the bandwidth will be increased. تمام؟ فهنا في trade off أيضا في الموضوع. Okay يا شباب? So maybe we'll stop here. We'll start our study for the common source low frequency response next class إن شاء الله. Be prepared for the quiz. يعطيكم العافية. See you Tuesday, Thursday إن شاء الله.
يا دكتور.
تفضل أنا موجود. تفضل.
I just missed the first minute of the lecture.